Hello. We've looked at the construction of a kind of descriptor of sort of short-term action sequences so that we can look at a sort of instantaneous behavior such as like a run or a hand wave or something like that. And what we would like to do now is see how we can use that descriptor as a way of indexing into a database of previously stored actions. Once we've indexed in that database, then we can say the action that we've recognized from that database is a particular action, and that allows us to say, well, we've identified it. So what that means now is that we need to find out some way of doing this kind of matching algorithm. Well, the basic matching algorithm is just a kind of convolution type algorithm. As we saw previously, we had a descriptor of an object, of an action, okay, from one particular sequence, and we indexed over the 4 components of the optical flow, and we also indexed over the pixel values, and this is for a given time frame. And so this is a description maybe of a new video sequence that we've just got, and that's the descriptor that comes from a single frame. Here is a corresponding single frame of sequence B, which is stored in our database, and we're just going to match frame I from the first sequence with frame J of the second sequence. If the two are identical, then this would have a very high matching score. If the two are not identical, then it'll have a very low matching score. And so consequently, this matching function right here gives us some idea of how well the two sequences match for these particular frames. Okay, so this is for frame I and frame J. Well, how well does that sort of work? Well, we have an example right here of, for example, the football player running, where we have the ith frame matched with the j frame. And this kind of encodes how well that matching takes place. So the bright red colors mean that the 2 pixels, or the 2 frames, sort of this frame and this frame, actually match very well. And the blue color saying that, you know, this frame and these frames do not match very well. So this is a kind of color representation of the different values that you get for this matching function. So we look at this and we kind of say, right, well, I can certainly see that there's some frames that match particularly well, and I see that there's a little bit of a sort of structure in here. But one of the things that we have not taken account of here is the fact that actions are not single frames long. Actually, they're a sequence of consecutive frames. And we haven't taken advantage of that little extra piece of knowledge. So that's what we're going to do next. And in fact, rather than matching a single frame, we're going to match a little window of frames together. And we're going to take those matching scores and we're going to combine them together with a kind of weighting function, again in a little convolution function, effectively that sort of says, you know, these should be consecutive frames. If you know, this frame matches, you know, these two, then the next frame, this and this should match because the frames happen one after the other. So it kind of takes account of how much action is happening in consecutive time frames. And again, we'd use a convolution with a weighted sum function right here, where we convolve and add together all of the consecutive frames. But we take account of a kind of convolution function, a little filter that's sort of geared towards that consecutive frames. In fact, we can see that little convolution filter right here, where you can see it sort of has a lot of weight along the diagonal, which emphasizes consecutive frames. It's a little bit blurred off the diagonal, and that's partly because people, when they perform actions, they don't perform it at exactly the same rate every time, either because it's different people with slightly longer legs when they're running, for example, or just because of natural variation. So that has pretty strong weight along the diagonal, but as you get off the diagonal a little bit, it has smaller weights. And also the further you get away from the sort of centered area, the larger the weighting comes because of the greater uncertainty in the matching. Anyway, so that's our little kernel function for doing our convolution. So we do our weighted sum of all of this, and that gives us a better idea of really how well these frame I and frame J match together, taking account of not that particular frame only, but also the frames before and the frames after in a weighted kind of way. And so by applying this particular convolution function to this original data, that's what gives us this particular data right here. And now you can see this sort of structure quite easily here. So this would be the tracking of one person in consecutive frames along here with something in the database along other consecutive frames. And you can see that the score values are really quite high along the sort of black line that I've drawn out right here. What that means is we've got a pretty good match, that whatever action this person is doing in this new video, it matches pretty well with what's happening here. Now, another thing you might notice right here is that it's not just good action matching along here, but also there are these other matching. So saying that, you know, this frame here not only matches this frame, but it also matches this frame and matches this frame, matches this frame. You might ask yourself, well, why is that? Well, I think the answer should be pretty obvious if you're thinking about what the person is doing. If they're running, this is a repetitive kind of action. And so, you know, every 30 frames, you know, I will be in this position, and then 15 more frames I'm in this position, and then 15 more frames I'm back to the same position. So every so often I will be in exactly the same position, and therefore my optical flow will be the same, and therefore also the descriptor will be the same. So when you do the matching, you'll get a good matching score. And so that's what we're seeing here right here is the different time alignments between the new sequence right here and the sequence that's in the database. Well, what can we do with that kind of descriptor? Well, we've got a couple of examples right here. One is of a tennis player and the other is of the running sequence that we've had before. Okay, where, for example, in the top row we see the new video sequence, and in the bottom row we see the sequence which has been extracted from the database that has the best match. And you can see, while there's slight differences in the particular pose and certainly differences in the clothing, you can see the general action is kind of about the same in terms of the sweep of the arm. Our analysis that we used using the optical flow didn't pay any attention really to the colors of the data. What it was looking for is the changes in the data, the motion. And so therefore, we can easily extract a person who's wearing one thing, match it against a person who's wearing something different. It's the action itself that's the important bit, and you can see that they match pretty well between the two sequences. And similarly between the two football sequences as well. So if we look at the original paper, they've produced analysis for 3 different sets of sort of short-term behaviors. One is a ballet sequence where they had, I think, 16 different ballet motions. Tennis where they have 6 different, and football was 2, 4, 6, 8 different motions. And this is a confusion matrix that records how well their algorithm worked on that particular data. And so what you've had right here is a list down the, let's say, the left-hand side of the particular sequence that's come from the test data, and then this is the a record of the sequences that are withdrawn from the database. And fortunately, you can see there's a really strong performance down the main diagonal. That means that it's correctly extracted the true sequence, whatever. But there are a few cases of where it extracted a different sequence and basically mislabeled the observed behavior. But on the whole, we notice it has a really strong behavior going down the main diagonal, and that suggests that this particular algorithm has worked very well for identifying these short-term behaviors. Well, to summarize this little bit of lecture sequence, what we can see that what we've looked at is really a short-term action representation. It's sort of based on the optical flow, and it's geared just for recognizing things that take place over a second or two, some sort of just a brief motion or whatever. And these can be the cornerstones of putting the individual pieces together to look at a larger sequence of behavior. But really, all we've looked at here is just the short-term kind of aspect. In order to do that, what we're looking at is how is the person moving with respect to their body, rather than where the body is moving with respect to the whole scene. And so consequently, we needed to stabilize that body, so we can just focus on the changes relative to the body, and then we used an optical flow type method for describing those relative changes. And once we put all of that together, we have a pretty good way of representing the temporal structure, just sort of the short-term collection of all the individual actions that are taking place. And as we saw from the confusion matrices, it worked pretty well. Now, I mentioned before, one of the problems that we have to deal with is the fact that it's viewpoint dependent. And so a person doing an action here looks entirely different from a person doing an action right here. This type of representation would not work well. For something like that, we could either learn two different models, or we could use some kind of a three-dimensional body model. But we're not going to do that right here. There's another issue that we haven't mentioned, and that is, again, because we're matching image data, if you have anything which changes the image, then it's not going to match. And scale is another example of that. So if a person is at one point in the visual field, there'll be a certain size. If they're at a different point in the visual field, there'll be a different size. And again, things won't match very well. Again, this means that you might need to have multiple examples in your database of people doing the same motions but in different positions in order to get the different scales. Anyway, thank you very much.